What I hope to introduce you to in this video is the notion of a transformation in mathematics. And you're probably used to the word in everyday language. Transformation means something is changing. It's transforming from one thing to another. So what would transformation mean in a mathematical context? Well, it could mean that you're taking something mathematical and you're changing it into something else mathematical, and that's exactly what it is. It's talking about taking a set of coordinates or a set of points and then changing them into a different set of coordinates or a different set of points. For example, this right over here, this is a quadrilateral. We've plotted it on the coordinate plane. This is a set of points, not just the 4 points that represent the vertices of the quadrilateral, but all the points along the sides too. There's a bunch of points along this. You could argue there's an infinite, or there are an infinite number of points along this quadrilateral. This right over here, the point x equals 0, y equals -4. This is a point on the quadrilateral. Now, we can apply a transformation to this. And the first one I'm going to show you is a translation, which just means moving all the points in the same direction and the same amount in that same direction. And I'm using the Khan Academy translation widget to do it. So let's translate this, and I can do it by grabbing onto one of the vertices. And notice I've now shifted it to the right by 2. Every point here, not just the orange points, has shifted to the right by 2. This one has shifted to the right by 2. This point right over here has shifted to the right by 2. Every point has shifted in the same direction by the same amount. That's what a translation is. Now I've shifted, let's see, if I put it here, every point has shifted to the right one and up one. They've all shifted by the same amount in the same directions. That is a translation. But you can imagine a translation is not the only kind of transformation. In fact, there's an unlimited variation. There's an unlimited number of different transformations. So for example, I could do a rotation. So I have another set of points here that's represented by quadrilateral, I guess we could call it CD or BCDE, and I could rotate it. And I would rotate it around a point. So for example, I could rotate it around the point D. So this is what I start with. Let me see if I can do this. I could rotate it like, actually let me see. So if I start like this, I could rotate it 90 degrees. I could rotate 90 degrees. So I could rotate it like, that looks pretty close to a 90-degree rotation. So every point that was on the original, or in the original set of points, I've now shifted it relative to that point that I'm rotating around. I've now rotated it 90 degrees. So this point has now mapped to this point over here. This point has now mapped to this point over here. And I'm just picking the vertices because those are a little bit easier to think about. This point has mapped to this point. The point of rotation, actually, since D is actually the point of rotation, that one actually has not shifted. And just so you get some terminology, the set of points after you apply the transformation, this is called the image of the transformation. So I had quadrilateral BCDE. I applied a 90-degree counterclockwise rotation around the point D. And so this new set of points, this is the image of our original quadrilateral after the transformation. And I don't have to just, let me undo this. I don't have to rotate around just one of the points that are on the original set, that are on our quadrilateral. I could rotate around the origin. I could do something like that. And notice it's a different rotation now. It's a different rotation. I could rotate around any point. Now let's look at another transformation, and that would be the notion of a reflection. And you know what reflection means in everyday life. You kind of imagine the reflection of an image in a mirror or on the water. And that's exactly what we're going to do over here. So if we reflect across a line. So let me do that. So this, what is this? 1, 2, 3, 4, 5. This not irregular pentagon. Let's reflect it. And to reflect it, let me make a line like this. I could reflect it across a whole series of lines. Whoops, let me see if I can. So let's reflect it across this. Now what does it mean to reflect across something? One way I imagine is if this was, we're going to get its mirror image, and you kind of imagine this as kind of the line of symmetry, that the image and the original set of the original shape, they should be mirror images across this line. We could see that. Let's do the reflection. There you go. And you see we have a mirror image. This is this far away from the line. This corresponding point in the image is on the other side of the line, but the same distance. This point over here is this distance from the line, and this point over here is the same distance, but on the other side. Now, all of the transformations that I've just showed you, the translation, the reflection, the rotation, these are called rigid transformations. And once again, you can just think about what does rigid mean in everyday life. It means something that's not flexible. It means something that you can't kind of stretch or scale up or scale down. It kind of maintains its shape. And that's what rigid transformations are fundamentally about. If you want to think a little bit more mathematically, a rigid transformation is one in which lengths and angles are preserved. You can see in this transformation right over here, the distance between this point and this point, between points T and R, and the distance between their corresponding image points, that distance is the same. The angle here, angle RTY, the measure of this angle over here, if you look at the corresponding angle in the image, it's going to be the same angle. So you might, and the same thing is true if you're doing a translation. You can imagine these are kind of acting like rigid objects. You can't stretch them. They're not flexible. They're maintaining their shape. Now, what would be examples of transformations that are not rigid transformations? Well, you can imagine scaling things up and down. If I were to scale this out where it has maybe the angles are preserved, but the lengths aren't preserved, that would not be a rigid transformation. If I were to just stretch one side of it, or if I were to just pull this point while the other points stayed where they are, I'd be kind of distorting it or stretching it. That would not be a rigid transformation. So hopefully this gets you, it's actually very, very interesting. I mean, when you use an art program or actually you use a lot of computer graphics or you play a video game, that most of what the video game is doing is actually doing transformations, sometimes in 2 dimensions, sometimes in 3 dimensions. And once you get into more advanced math, especially things like linear algebra, as a whole field, it's really focused around transformations. In fact, some of the computers with really good graphics processors, a graphics processor is just a piece of hardware that is really good at performing mathematical transformations so that you can immerse yourself in a 3D reality or whatever else. So this is really, really interesting stuff.